my great pleasure to welcome you all to today's event, which is organized by the Quantum Science Center at EFL. And I want to say a few words about this event. This English lecture actually is quite a special event for us because it's organized only once or twice a year. So we invite people who are very famous in the field of quantum hardware, software, in quantum computing, and so on. So I'm very happy that this time we have somebody who is focusing on hardware and on photonics, and this is a topic which is very dear to my heart. But what I want to also mention is that the Quantum Science Center, aims to bring together this quantum community at EFL at events like this. And one of our core missions is, of course, to bring together the scientists with students and PhD students. And now, because students are also at the very core of our mission, what we decided to do today is, maybe some of you know this from music. Before you have the main act, you have a band before, right? So, in the spirit of science, we decided to have some students from EFL giving 3 short talks, 3 minutes. They were very courageous and speak before Marko. So the first speaker of today is Yasin Koyas from FOSSA, so the Photonic Systems Laboratory, and she will speak about standardized integrated nonlinear building blocks for thin film lithium niobate. All talks will be 3 minutes long, no questions, so it will be a rooster, and then later on we are going to continue with the main act. Thank you very much.
Thank you for the introduction. The topic today for me is standardization for thin film lithium niobate platform. And I would like to start with our motivation on working with this platform. So bulk lithium niobate has been commercially used for decades for electro-optic modulators and for nonlinear crystals. But very recently, thin film lithium niobate has become available in the form of low-loss wavegates. And what this means is, strongly confined light is propagating through a very high nonlinearity medium. And more than that, it's a ferroelectric material, so it can be periodically pooled. And in this case, the pooling period is a design parameter that is defined lithographically on metal electrodes. And all in all, we can allow highly efficient frequency conversion processes within this platform. With these properties and many more, the horizons and applications for thin film lithium niobate are very versatile, from atomic clocks to gas sensing and to many, many things. There are many things that you can work with thin film lithium niobate. But for all of this, exploiting the properties of thin film lithium niobate in view of a large-scale implementation is essential. And that's what we are working on. We are looking for compatibility with the existing platforms in a scalable and reproducible way. With our project partner, CSCM, we are trying to offer essential nonlinear building blocks in the TFLM platform in view of a commercialized foundry service. Here, in the next minutes, I will focus on second harmonic generation. In the design, we calculate the pooling periods and the conversion efficiency. And we focus on different waveguide cross-sections. As a result of this design, it is fabricated in CSCM and then characterized in this bench here. Then, by using the input from the fabrication and from the measurement, we consider the tolerances on these waveguides, and we aim for the validation of our designs for a standardized platform. Here are some of the results. We identified the designs for broadband operation or for narrowband operation with a range from 10 nanometer to 1.4 nanometer. We experimentally verified our designs of 4 nanometer bandwidth and achieved a conversion efficiency of 150% per watt. It is modest for lithium niobate, but still quite high considering other platforms. We also experimentally repeated our tolerance analysis and saw that the performance in terms of the SH peak position is close within the chip that we are investigating. We also see variations due to imperfect polling and between the wafers. But all in all, even though I only spoke here about second harmonic generation, we consider different building blocks. We are looking for ways to further improve the performance of our building blocks through optimizations on polling and with polling period engineering. With this, we can compensate the effect of tolerances. But lastly, but most importantly, actually, the standardization continues on CSCM with wafer scale polling and its implementations of the building blocks, hopefully one day into a PDK in a foundry. So there are many things to do. Thanks for listening.
Hello, can you hear me? Great. I'll start. Okay, today I will share our recent result on the electro-optic frequency comp in video handling. And so the first question will be, so what is frequency comp? Then why we want to do frequency comp? And I think everyone is familiar with laser, like, I don't know whether you have a laser in here, but for laser pointer, that we can create one single frequency, very quiet, single color. And what is frequency comp, optical frequency comp, is that we have multiple lasers, that a bunch of them, then we can create an array of lasers with different colors. And more importantly, for frequency comp, it is more than an array of lasers, because each laser line, they are phase locked to each other. Their coherency is mutually locked. So that means frequency comp is important and useful. We can use this kind of mutual information between different comp lines to do like from sensing to communication or to LiDAR, etc. And let me introduce a bit of history and how this frequency comp overview could be. It was since pretty interesting, the end of last century, 1993, the first frequency comp was actually invented as an electro-optic comp that people put a lithium niobate into an optical cavity and modulate it to generate comp. But soon, at 1999, the invention of current length comp that can get much broader than the electro-optic comp quickly dominates the field. And this field, the current length comp changed the whole metrology because it can octave, etc., and it was recognized at the 2005 Nobel Physics Prize. And then people started continue working on that, including our group, trying to minimizing this kind of current comp into chip scale. And 2019, a central work for Marko Lonchar's group is people have minimized that electro-optic comp into chip scale devices by shrinking down the optical mode scale into micrometer scale. In this way, the electro-optic interaction is strongly enhanced, so can get much broader comp than the bulk realization. So this marked a renaissance of interest for this comp. And for our approach, we are interested in the electro-optic comp also. So we are trying to push this forward, and we want to ask how much broader can we get. So this is a work divided into two parts. For photonics part, we know that for lithium niobate, there was an unwanted effect of birefringence. That when the modes cross by in the bands, it transfused into other modes. So we developed a lithium pentaplate, a close cousin with lithium niobate with 17 times less birefringence. With that, we can solve these birefringence limits. And also for the microwave, EOCOM is a microwave photonic plus is the merging devices. But we only need 160 frequency. So we'll do some microwave engineering, including a micro resonator to enhance the response of specific frequency. With that, we can attain 16 times higher power efficiency than that, which means here the red line is a comparison between our non-resonant device, the blue line is our resonant devices. We can get 4 times broader to 400 nanometers. Then it's the next step. So takeaway information is we have an interesting thing to play with. A comp is very small, less than a fingerprint. And what we can try? First thing we want to do is try some sensing, because sensing is a great application for this kind of coherent structure. We can do full FSR scripting. The more important question in my mind is, we are very low efficiency, that's something we are hiding. And we want to improve it. We want to see whether we can get octave spanning. In this way, the EOCOM can get much more application than we can expect it. Thank you.
So hello everyone, welcome to my presentation on photonic integrated terahertz devices. So I'm interested in the frequency range below optics, which is referred to as terahertz gap historically. In this frequency range, the absorption of materials in optics starts to dominate. And when it comes to electronics, we start reaching the cutoff frequency because of the RC constant. And at the same time, there are many applications that are interested in this field, from metrology to 6G to even astronomy, where we are searching for organic molecules in outer space. And their fingerprint lies in the terahertz frequency. So from Maxwell equation viewpoint, to generate terahertz, we need a charge point density that has to oscillate at terahertz frequencies. And there are many different schemes that generate these charges, from spintronics to photomixers. But I'm interested in fast nonlinearity, where we are exciting below the band gap. So we are working with lithium niobate, and the state-of-the-art metal system is really bulky components on optical tabletop, and we want to have really compact devices all on a chip. So for nonlinear optics, phase matching is a very essential ingredient. In phase matching, the source of the radiation and the radiation itself have to propagate with the same velocity. And this is at least in collinear phase matching. And to show why this is fundamentally not possible in bulk material, if you consider any optical mode, which is at some frequency, we want to generate frequencies that is order of magnitude different. So because of dispersion, this is not possible using the same material. So what we did in my work is that we sacrificed the spatial overlap between the two modes, meaning that these two modes will overlap with the material differently, and by some smart design, we can have nearly perfect phase matching for a very broad band. Now, to prove that this is the case, we deposit an antenna at the end of what we call the transmission line, and then we measure few cycle pulses with broadband above 3 terahertz. Now, to show how versatile this platform can be, we use the transmission line itself as a cavity to implement some selectivity on the frequency that we emit. And recently, we are working on array enhancement. So you can see that by having array structures, you can have something closer to continuous wave, which makes this platform very versatile. And very recently, with my colleague Shui, we showed that the same device can be used to both generate and detect terahertz, and it can both work in both O band and C band. So this will have hopefully many different applications. So with this, thank you very much, and hope you will enjoy the talk.
Thank you to all the speakers. I really think that they did a tremendous job, and I mean, it takes some courage, right, to speak before Marko. So I think also from my side, congratulations to all of you. And now it's of course my greatest pleasure to welcome Professor Marko Lončar here at EPFL, who kindly accepted our invitation to see our labs and give a talk today. And I want to say a few words about Marko for those of you who perhaps don't know him so well. Obviously, Marko is world renowned for his pioneering work in nanophotonics, in integrated photonics, and perhaps most notably when it comes to working with those materials that are very difficult to work with, such as diamond and lithium niobate. And you know, I stalked him a little bit on the internet, and I found some things that I knew and some things I didn't know. But his academic journey started at Caltech, where he did his PhD with Axel Scherer. And actually, he worked on 3-5 materials. So he used to be an ALGAS, INGAS guy. And during his PhD, he did work in photonic crystals and making lasers from photonic crystals in these 3-5 materials. And actually, it turns out that in his PhD work, in 2002 or so, they published the first laser from a photonic crystal which has the lowest power threshold. So, you know, already back then it kind of crystallized that he was a guy who really liked to do devices that work well, have good performance in terms of metrics and all of those things that matter also outside of the lab. And I looked through his thesis and I noticed that already back then he used the ion beam etching, you know, as a technique to etch the hard mask that was then used to etch this photonic crystal. So I guess this helped him later along the way for those of you who do fab of these materials. And interestingly, afterwards, he remained quite loyal to 3-5, so he moved to the group of Federico Capasso, where he stayed with the 3.5s, but he moved to another frequency band, namely in the mid-infrared, where he was researching some cascade lasers. And then later he became a faculty also at Harvard in 2006. And I guess, I mean, this is what I'm interpreting now, that during his tenure track, he started looking for some other materials and found, materials that are interesting in terms of linear and nonlinear and quantum properties, and found diamond and, nitrogen vacancy centers at the time were kind of just starting. So what they developed in a paper in 2010 was basically single photon emitters from nitrogen vacancies in diamond that were etched from a single crystal of diamond layer. So that was a big splash at the time, and I was reading through the abstract, and actually already then I could tell that probably this platform will have a lot of in the future. I guess you're going to hear a little bit more about it today. Yes, and I'm guessing that learning how to etch these difficult materials like diamond kind of brought him then to this innovate, and I guess this is maybe the work that most of you know him for. And of course, he demonstrated, and he and his group demonstrated modulators, electronic frequency combs, pulse generators, and so on. So the stuff continues. And so I stop here, but not before saying that this, earned him a lot of recognition, many prizes, and that I won't list here. But I would just mention kind of on a more personal note that I know Marko is someone who really fosters diversity, not just in terms of gender, but also in terms of age and seniority. And actually when I told him about this idea to have this, opening act with the students, he was very supportive. So on behalf of all the students, thank you, Marko, for allowing this to happen. And now, I won't keep the audience waiting longer, so I'm looking forward to it.
Well, thank you so much, Christina, for inviting me. It's been a great pleasure. I always enjoy coming to PFL. This is, I don't know, fourth, fifth time maybe, and I find, well, this is recorded, so I should be careful what I say. I find sometimes I have quite a few friends. I was going to say more friends than at Harvard, but okay, I didn't say that. It's really nice to see friendly people. Not that people are not friendly, but friends that I've seen in a long time. And especially, this is a great honor. I didn't realize this is such a, so like twice a year, so it's a great honor, Christina, to think of me. And yeah, thanks to everybody for showing the labs today. It's been great fun. Learned a lot, and looking forward to another day and a half. So today I'd like to share, first of all, let's find the pointer. We can do this. It's modern technology. Laser pointer. Good. Perfect. So before I start, I'll tell you a little bit about optical interconnects. Before I start, I actually do need to say that I'm also involved in this startup. This is Harvard's request for conflict of interest reasons. So it is, make sure that maybe I'm overselling it, maybe I'm not, so take it with a grain of salt. I'm making a sabbatical this year, so I'm spending about 60% of my time here. So this is Harvard's request. So what are optical interconnects? Basically, there's very many ways to define it, but just like classical optical interconnects that are used to connect computers across the world, even shorter distances, basically quantum optical interconnects are devices and processes that will allow transfer, in this case, of quantum information. And I say often, I actually need to be able to establish and distribute entanglement in order to essentially connect quantum systems. So it could be ideally quantum computers, once they become more prevalent. In the meantime, quantum sensors and quantum computers, perhaps there's some of the things we're looking at. And light is actually really good at connecting things because it's very low loss and high bandwidth. And so, of course, that's why it's used in optical communications. Backbone, fiber optic networks forms the backbone of internet. But also, we benefit from highly developed optical communication technology, and also also infrastructure. And on a personal note, I'm really excited about quantum optics. I'm actually a classically trained engineer, and quantum optics is something that I find very fascinating and interesting. But in the back of my mind, if this quantum thing never hits off, we'll have amazing optical devices, very low loss, very fast, new materials. I'm really excited about it. In fact, lithium niobate, when we started, was developed so that we can actually make frequency converters, like similar to the ones that quantum students were discussing first student, for single photons, and then only then we realized there's still these amazing opportunities in plasma. So some examples of quantum interconnects, and these are selected from kind of studied up my code today, is basically photonic switch networks. So here's an example of photonic switch network in your favorite interior photonics material that could be used to deliver and collect signals to, let's say, trapped ion quantum computer. In broad, so strictly speaking, coherent light that we use to control these systems, maybe doesn't satisfy this requirement for establishing entanglement, but it's very important to actually be able to deliver many signals in parallel to trapped ions and trapped ions. But also on the other hand, it's important to collect the light they emit. This is obviously with the other state. On the other hand, there's other favorite quantum computers, the superconducting quantum computer, and there's amazing work I'll learn about here today. And so there, if you want to connect them to internet, or if you want to be able to access them remotely, they actually, you need to make sure that you can make transduction between microwave domain and optical domain, meaning these devices actually communicate, or different qubits on a superconducting quantum computing chip, communicate by sending around microwave photons. But if you really want to go a long distance, these microwave photons need to be converted to optical wavelength range to be telecom wavelength range so that we get low loss connectivity. And then, because you're sending single photon fields or more importantly, entangled photon states that are really fragile and sensitive to loss, these links actually cannot be very long because optical fibers do have finite propagation loss. And so therefore, this kind of ideal quantum repeater, which is a device that would allow you to extend the reach of quantum communication channel is important. To do all of these things, there's quite a few challenges, and I listed just a few here. First, still we still don't know what is going to be the future, the qubit of the future, right? There's so many different qubits considered for computing, photons, microwave photons, superconducting qubit, various types of junctions, spin qubits, so on and so forth, trapped atoms, trapped ions. And so it's important to consider, and if you start, when this, if ever this actually, if this kind of focusing of the field happens, maybe we'll start thinking about how to connect them. So I think it's never too early to start thinking about connecting these different qubit platforms to light, but then there's so many of them, so which one do you start with? They also operate a very wide frequency range, like as I said, superconducting qubits operate at about gigahertz microwave frequencies, telecom photons are at 1.5 microns, most color centers are invisible, trapped ions often communicate, they have important transition lines even in UV. So you go from gigahertz to petahertz frequency range, which is actually not easy to convert. You really need high performance devices for that. And then length scales also go from, chip scale length scale, where maybe you want to connect to spin qubits in diamond or something else, to maybe like laboratory scale links to connect different quantum computers, to make modular quantum computers, to even, if you're more ambitious, to continental scale links if you're really interested in building quantum internet. And so, but why do we want to do this actually? So here's a few reasons why. I already hinted upon this, just want to drive home some of these messages. Like, why do we want to connect superconducting qubits to light? Right? So one application that actually we've been talking a lot to almost all major superconducting quantum computing players at the moment is this quantum transduction here. Also at the BSC Lab, there's very nice work in this area. And so one of the issues that this field is facing that actually, so these superconducting qubits operate at low temperature, typically 2 millikelvin. Number of qubits that you need to have large number of logical qubits, it's actually giant. And it simply doesn't fit in the dilution refrigerator. And more importantly, the cooling power into these dilution refrigerators is not sufficient to cool the whole thing down. Especially when each qubit has many different like coaxial cable links that are going from 10 millikelvin to room temperature with some attenuators in between. So this actually increases the heat load. So this is a problem. So the idea already that's emerged in theory and also experiments is to connect these things to essentially have small, you can think of them as computer cores. Like your microprocessor, for the similar reasons, even though number of transistors on the chip goes up, but actually they cannot make, because of heat dissipation, actually the architecture that's being used these days is really one of multi-port. So you can think of it as this being one large qubit processor, quantum computer that consists of 3 different cores. And in order to connect it, as I said, you cannot use microwaves, because microwaves at about 5 gigahertz, if you go to room temperature, you're susceptible to noise, so you need to go to light, and that's when you transduce it. Now, I already mentioned this, and I'm going to belabor this point, is that atom-based quantum computers, here's an example from a work of my colleague Michel looking at Harvard, already have hundreds, I haven't checked what's the latest number, but maybe 1,000 of trapped atoms. The way they're addressing each of them, right now they're using stop modulators, but that actually doesn't scale so well. I mean, they're also, so they're able to do amazing stuff for now, but if this technology is going to scale forward, they already started looking into essentially photonics approaches to deliver control signals and also collect perhaps the emitted signals, perhaps using metasurfaces. My former postdoc advisor Federico Capasso's favorite topic, and actually there are some examples of that already. Similarly, for ion-based quantum computers, we already talked leading players there. They, for similar reasons, they're interested in actually photonic interface to these systems. So that's where these integrated photonics comes in. And then if you want to be a secure quantum network, and this is just from the European flagship program, or if you're interested in distributed fence sensing, which is maybe a little more close term, where you take advantage of entanglement between sensors that are separated by large distance in order to improve sensitivity of the system. In this case, increase the aperture of this synthetic radio radar. You need to be able to distinguish entanglement across long distance, and because typically you don't be doing this using optical fibers, but they're lossy, so basically you will need this repeater, right? So there's different types of repeater. I'll talk to you a little bit today about memory-based quantum repeaters that are able to synchronize signals coming from different quantum emitters in order to essentially improve the scaling significantly. So this hopefully motivates why we are interested in quantum optical interconnects. More honest, maybe your argument, how I originally started, I was fascinated by quantum, but I'm not this guy. I wasn't going to build a quantum computer, so I was trying to figure out what can I do with this field. So I came up with some of these interconnectivity problems, which actually turns out to be quite challenging. If everything works, maybe one day we would be able to build this quantum internet, and maybe this would enable, like, let's say, light quantum computing. That's one of the topics that is quite interesting. Distributed sensing. There's also, typically this is mentioned in context of secure communications, and there's definitely, skeptics in our community who think that there's other ways how to do this, to communicate securely, that maybe this is distributing entanglement is not necessarily needed, but I think in order to connect different quantum computers, different quantum resources, connect them to photonic clocks and whatnot, you would probably want to distribute entanglement states for which maybe you don't need to go from LA to Boston, but and smaller length state scales, I think it's really beneficial to look at these quantum networks. And this is also a small advertisement for NSF Engineering Research Center that I'm part of in the US, that's led by University of Arizona, that is looking to develop a quantum internet, basically. As an ambitious goal, but keeping in mind that these smaller goals are actually very, very important, very practical in their term. So this brings me a little bit to the outline of the talk. So first I'll tell you a little bit about, it's going to divide quantum repeater and quantum transducer. This kind of photonics for trapped ions and trapped atoms kind of follows a little bit the second part of quantum repeater discussion, which is quantum photonics. So this is kind of lumped in one topic. So first, tell a little bit about our progress in diamond quantum photonics with the goal of building quantum networks based on quantum memories in diamond. Just highlights, and maybe just bring everybody on the same page, talk a little bit about NV centers and silicon legacy centers, which Christina mentioned. Then I'll talk a little bit about quantum photonics in ivory to fix the problems of quantum memories in diamond, and there are many nice things about it, there are many problems. So we think that quantum photonics or larger photonics in ivory can actually address these shortcomings. And then towards the end, if time permitting, I would like to tell a little bit about the progress of quantum transducers that we are using to connect to quantum qubits to light. I did put some phononics there in the first quote, but most likely it's going to just slide or two because I probably won't have enough time. So the first topic basically is this kind of diamond, basically diamond quantum memories for quantum repeater demonstrations. And these are the people, past group members and current group members who have been involved in some of these developments and quantum sources. So basically, I'm not going to go into details of how quantum repeater works because then I will never get to other topics. So basically, the overarching principle is you have quantum memories that you can daisy chain and kind of essentially kind of relay quantum information from one memory to another, essentially, right? In order to establish entanglement across long distance, and then using teleportation protocol, you can send the state of interest from one end to the other end of the network. And for that, you need to couple quantum memories. So generic quantum memory is an atom that talks to light, but actually the probability of this process is not very large, so typically put atom in optical cavity. And then actually using light, we can talk to atom. Atom typically, if it's below a system, you can use this as a degree of freedom to store the quantum state, but more often than not, we have kind of auxiliary atom that is actually used to store quantum information that can couple to the atom that's used for communication, the one that talks to light. And this allows you to store, to have more coherent systems so you can actually propagate over longer distance. And so then this photon travels to another remote node of the quantum network. This is a very simplified protocol. So it goes for assets in the field. So basically, so we have another quantum node that has also quantum memories, has optical cavity, and has a qubit that is used to store information. And when this all happens, then this actually cascades. We can have like 10, 15 of these depending how far we need to go. Okay? And so there are, several kind of challenges here. Like first, we would like this to scale. So maybe like a few years ago, I would say trapped atoms are not going to work. I'm not going to say this because trapped atoms will be great, and so I'm doing trapped ions. But still, perhaps the leading platform people are considering this is our solid-state platforms like spin qubits in diamond in particular, but also there's spins in quantum dots and spins in silicon and whatnot, can be used as memory elements, and some of them ideally, particularly for photonics, those that talk to light are very interesting, so I'll focus attention today to qubits in diamond. Another thing that's going to come back later, because we're talking about solid-state systems, you'll see that actually not all artificial atoms that we are going to use are the same. Each real atom is the same, and they operate the same wavelength, which is great if you want to interface them. But in our case, actually, these two atoms will operate two different wavelengths, and that means you cannot interface them. So we need to find ways to fix this problem, and this is actually, there's two main approaches we are doing, and I'm going to briefly mention one, and I'm going to go into detail of the other. I already revealed that our quantum network is really based on color centers in diamonds, so this is this kind of similar, basically the same idea now with 3 nodes, and here I'm showing the nuclear spin, electron spin, socialist color center in diamond, and we use auxiliary qubits nuclear spin, power 13 or silicon isotope, and then we basically build them in the resonators that are not shown here. And we need very efficient interface between diamond resonator and fiber, otherwise we lose information, which is not very good. We also need to propagate in long distance, so we cannot use we better operate in telecommunication wavelength range where actually fibers are really, really good. So all of these things will come back later in talks. I just want to point out some challenges. Christina mentioned that basic NE center is perhaps the best known color centers now. There's some amazing work we're seeing today. Chris Graff's group about NE centers in diamond. It's essentially carbon lattice of diamond. You knock out one carbon atom, you replace it with nitrogen. Nearby carbon atom is missing, forms vacancy, and this thing becomes negatively charged by attracting one electron. It's actually negatively charged NE center diamond that people are using, and it's been in the workforce kind of this field for many years. And this is how it looks in the lab. This is a big diamond that's loaded with NE centers, and I'm shooting green laser pointer. Actually, I was going to bring this. Good thing I didn't, because I was told that you cannot bring laser pointer into Switzerland. And this definitely would work. But basically here, we're already doing a quantum experiment. We are taking green laser, we are polarizing NE centers in this diamond, and they essentially can start emitting single photons, but there's so many of them. NE centers they're beautiful from magnetometry, but they turn out to be really bad choice for quantum communication. I'm not going to go into details of it, I'll just say that in order to put them in a resonator to have very efficient communication protocols, you actually need to bring them close to surfaces of diamond, and they become very sensitive to charge fluctuations in the surface, which actually kind of renders them useless for quantum communication protocols. They're extremely useful for quantum magnetometry, sensing, and many other things. And if somebody in the audience solves the problem of surface kind of charge fluctuations, dangling bonds, and stabilizes NEs, I think the whole community will go back to NE. They are kind of the best center that we know today. It can operate at room temperature, but because of these problems, the community has shifted away from it. Instead, the community is working on so-called group 4 color centers in diamond. In our lab, we focus on silicon vacancy color center in diamond. So this is silicon atom that sits between two vacancies in diamond carbon lattice. And it's nice because actually it's not sensitive to charge fluctuations in the surface to the first order. It also doesn't have Stark effect, which is a problem when you need to tune it, but I'll show you some examples how to tune it. This is simplified level diagram for experts. I would just say that drawback of this system is that actually it has to be cooled down, and it has to be cooled down to ideally 100 millikelvin temperature, so it's a lot more expensive to do the work with this center than every center. And the reason why we need to cool it down is because spin is sensitive actually to phonons in the lattice. And this sensitivity of spin to phonons should be surprising, but actually the physics behind it is that silicon vacancy orbital degrees of freedom are really sensitive to 50 gigahertz phonons, which is this is the ground state of the system, separation between ground state level. And because of really strong coupling between spin and orbit, and if you haven't heard this term, you can think about this in the context of this kind of wrong quantum model of an atom, where you have electron circling around nucleus and it's spinning. So this kind of orbital degree, orbital magnetic field, spin magnetic field interact. And so that actually causes phonons to decohere spin. And so in order to fix it, you cool it down. Another way actually to think about this is actually you can use it also. You can use it to control this spin now using sound, which is quite interesting. And we actually have a whole area of research there where we use surface acoustic wave optimization crystal to control spins in diamond. I will not be able to tell a whole lot about this today. It seems like also the way I'm going, I will not be able to tell a whole lot about anything, but give me a signal when my time is approaching. Okay. So this is our cavity that after many years we finally figured out how to do. And this is my student Bart, who's actually now started a company to commercialize some of this technology. So this is diamond, we carved bulk diamond crystal. We designed this to have cavity mode. This is fine crystal cavity. So this is actually numerically calculated optical mode profile in this cavity. After we fabricate cavity or before, depending on the process, we actually implant color centers in diamond inside exactly the location, the center of optical mode. We do this by actually aperture implantation and precision up to 40 nanometers in all 3 dimensions. And then basically this can be very strong coupling, very high cooperativity, it's an important figure of merit in this business, between spin and photon. And in order now to talk efficiently between spin and photon, you need to have very efficient interface between macro world, represented by this optical fiber, and diamond nano world, if you will, silicon vehicles is the center. And for that, actually, we have developed in collaboration with Amazon Web Services, who are supporting some of this work, extremely efficient interface between optical fibers, like with efficiency about 90%. We probably want it to be like 99% eventually, so you don't lose any photons. And this, by the way, we are now using mostly classical communication because it's so good. Using this, we can demonstrate together with Michel Luque, and I should point out all of this work was done with Michel Luque power. This was important kind of demonstration for the field. This is the first time, if you will, this was like quantum communication supremacy demonstration that memory-based quantum protocols, quantum computer protocols can overcome so-called direct communication protocols that mean just like shoot photon across distance and hope for the best. So this is kind of important work in that regard. And then building on that, without going into details, there was a big group of big team, including MIT, Harvard, MIT Econ Labs, and here at Harvard and Amazon Web Services, demonstrated Cambridge area quantum links. In this case, was between lab and Michel's lab in the physics department and Amazon Web Services across the river. The direct distances are a couple of kilometers, but these fibers go mysterious ways over and below the rivers, and it was a miracle that actually this sequence worked as well as it did. But it's a very, very nice result that recently came out. So I'm not gonna, if you can't hear more about these protocols, you'll be sad, but I encourage you to read these papers. I mainly want to focus on devices and interconnectivity here. That was important. So I showed you cavities, I didn't show you how we do it. So just for those of you who spend time in clean room, keep it up. It's actually very, very important to be able to build devices. And so these are three different ways that we develop some, in our labs, some kind of adaptive from other labs that we use routinely now to make devices with diamond. One is anti-latching. I know there's a lot going on here at Optical in this regard. Actually, all three approaches I'm going to show you. So these are some devices that we make. We carve devices directly in diamond. We're going to go into details. And the challenge is the diamond, unlike any other photonics material, is not available in thin film form, at least commercially. So you need to figure out how to structure quality diamonds, which is actually a little painful. Another approach is based on so-called isotropic undercut, where we basically first etch into diamond crystal like this, and then we etch like that. And so that actually, an optimized gives very nice. This just shows the device after 5 hours. I don't know how much is your RIE. I covered it about $100, so about $500. So reactive ion etching time. You get the device that you want. And so this is kind of maybe the highlight of this process. These are actually been workhorse for us for a number of years. These are these freestanding diamond photonic crystal cavities that have rectangular cross-section because of this isotropic undercut. And the last device kind of system that we are using is developed by Sophie and Kazu is a great collaboration with Alex Hai in the University of Chicago. Finally, we have actually access to some very nice diamond thin films where we can make 2D, 1D photonic crystals quite nicely. And this is actually quite nice. In fact, our quality factors, which tells you how small the losses are in this material platform, in diamond are smaller than almost in any other material platform in visible wavelength range, which is actually remarkable given how, to some extent, primitive this process of making diamond film still is. So, this line, for those who know specialist quality factor, tells you how wide is this line, how wide is the resonance. If you work with a pendulum, it tells you how many oscillations you can have. It's roughly related to that. So the larger the quality factor, the smaller this line, the better you can store photon inside the resonator, the more stronger interaction with the spin inside the resonator. So we are very excited by this. We are looking forward to kind of continuing this collaboration and shifting to this platform. So this is kind of photonics that enable these kind of quantum networks. I briefly mentioned also that this issue with phonons in diamond, and so we also looked into ability, and I added this because I had some nice discussion talking to people here to study body about phonons or to like study them. So one way to get rid of phonons is to cool everything down at millicounters. Another way to get rid of phonons is to make phononic bandgap structures. So these are devices that actually prevent phonon, the reduced density of states of phonons, not of photons. The problem is because of much smaller speed of sound in material, these devices tend to have really small periodicity. But as Christina pointed out, if I like something in life, this is very difficult to clean the problems. So we decided to go ahead and make these phononic crystals, and you can see here, these dimensions are really, really small. So for your unit cells, 100 nanometers, these standards are on the order of 15 to 20 nanometers. The whole thing is about 20 nanometers thick. And they do have phononic bandgap at 60 gigahertz, basically. So they prevent phonons at 60 gigahertz frequency to exist. There's no phonons ideally at 60 gigahertz in this structure. Of course, that's never the case because it's not infinitely long. And with that, without going into detail, we were able to show that we can extend coherence of orbital degrees of freedom. We can suppress phonon-driven processes, but we actually still working to show that the set has positive impact on spin. It's a challenging measurement. We think the answer is yes, but it's a challenging measure. So in this departure into phononics, I just want to go back to our color sensor, silicon vacancy color sensor, and photonics, and tell you a few problems with that. Right? They already mentioned up front. And one of the problems is inhomogeneous broadening, which means because each of these silicon vacancy color sensors sits in different part of the diamond, they have different strain environment. Therefore, they are actually not all emitting the same wavelength. And you can see some kind of crazy distribution. This is very frequency gigahertz. I guess we lost this. Oh, here we go. Or not. Okay. So this is, between two different samples, variation within a sample can be like 50 gigahertz. So you can have two atoms, quote unquote, that are 50 gigahertz apart. They will never talk. So we need to fix that. One way that we've done over the years is using strain. The reason why they are broadened homogeneously is because there's strain variations in diamond. So solution is to strain them even more so that the small strains actually doesn't matter anymore. So we pre-strain them using different approaches, and we were able, as this graph shows without me going into details, to take two silicon vacancy centers and apply strain using these cantilever structures. We were able to bring them together. And we can do this with many, many devices, I'm sure. But this is a little challenging, MEMS approach. We would like to do something a little different, as I'm going to show you. Another problem is that actually photons emitted by silicon vacancy color sensors are slow. This is determined by, or rather they're long, on the order of 20 nanoseconds. And also, if you want, we use, which is kind of glossed over, we use so-called timing qubit encoding of quantum information in these quantum protocols. And the length of the timing qubit given by how long it takes to prepare silicon vacancy in a particular state is on the order of 100 microseconds. So your communication rate, if this is the case, can never be bigger than 10 kilohertz. Right now it's probably a few hertz. So that's a problem because it's always going to be slow. So we need to address that as well. And third, as you see, like I mentioned this also, these emitters operate in visible wavelength range of 737. So we need so-called quantum frequency converters that will take us to 1300 nanometer range or 1500 nanometer range. And some of the work that our first student speaker today was discussing is directly related to this, actually try to do frequency conversion of photons. So the way we think we can actually address this is to use these kind of photonics platform that can correct for all these problems. Okay? And so the photonics platform would have first, it will have a bunch of, we call this switch fabric or spatial switches. These are combiners. They'll take a bunch of quantum memories that are here. These are diamond quantum memories. And they will multiplex them with the same input fiber. So this is just a bunch of beam splitters on chip that you can reconfigure. They are active beam splitters. You can apply voltages to select which memory talks to the fiber. So that's one thing. So we need a bunch of switches. Then we need, actually we're going to use phase modulators, and show you how, to correct for this. Okay? We will send single photon fields through phase modulator, apply RF signals to it, and shift the color of light left to right so that all silicon vacancy photons have similar wavelength after everything said and done. And then thirdly, we would like to have a platform where actually we can also do frequency conversion in the same chip, which is not illustrated here, but maybe you can envision one more device here that also does this frequency conversion. And so I'm sure you'll be shocked to hear after hearing 3 talks on lithium niobate and the opening that the platform we think it really can solve all of these issues in lithium niobate photonics platform. So that's the next thing I want to tell you about. These are students who have contributed to quantum aspect of lithium niobate photonics platform. We have a lot of people working on classical aspect of lithium niobate photonics. And so for those of you who have not heard about lithium niobate, let alone lithium, okay. My computer was me. Here we go. This lithium niobate is an old material. It's been around for decades, and it has been used in optoelectronics as well as quantum optics for that period of time as well. This is kind of atomic structure of it, and basically it's interesting, particularly because of this second order nonlinearity, which manifests itself as ability to mix optical photons with either microwave photons or other optical photons, which gives rise to devices like optical modulators, as shown here, or kind of photon pair sources using second-order optical nonlinearity, or a turn 1064 nanometer laser to 532 nanometer laser by process of second quantum generation that was eloquently discussed by one of the students. And so, just to make sure everybody's again on the same page, brief discussion of modulator. Basically, what modulators do and why they're so important, and you use them every day, knowingly or not. They're used to encode information that comes from electronic computer, that everybody uses, to impart this information in the form of ones and zeros onto optical carrier, essentially go from electrical domain to optical domain. So this is electro-optic transducer in classical shape, if you will. And then this optical signal is sent over fiber across long distance, and then it's received by the detector and goes back to the electronic computer. So these are classical optical interconnects that connect to classical computers. Okay. And this is how it's actually done. This is just one level below. Each of these modulators actually is basically Mach-Zehnder interferometer. These two blue things are waveguides, optical waveguides. This is beam splitter, this is beam splitter. And in one of the arms, often both arms of Mach-Zehnder, we put actually we put electrodes. We apply electrical signals to change refractiveness of the material, change the speed of light. So the two signals that are split at this point, one goes up, one goes down. When they meet here, they interfere destructively and constructively, and light goes up and down. Okay, so this is a modulator. You see how much time do we have actually?
I think, like, how much time do we still have? Like 10 minutes or so?
Okay. And then 15 minutes question, right?
Yeah.
Okay.
We have time.
We have time, yes.
Don't say it. You'll get dinner here. Okay, all right. So maybe just to do service to. So what is the issue with these things? And you know, you already know what the issues are and what the solutions, because you had the wonderful talks before me. But the issue is these components actually, we realized they bought lithium niobate crystals because people didn't know how to fabricate devices inside it for a long period of time. And so therefore they're very big, they're like this big. They have a limit in how fast they can operate, and they have actually required quite a bit of bias, quite a bit of voltage, probably 5 to 10 volts at 30 to 40 gigahertz. So it's very expensive in terms of money, it's expensive in terms of energy you need to have to actually drive these. So the idea was, can you miniaturize them? Can you do what people do in silicon photonics, silicon nitride photonics, gallium phosphide photonics, and whatnot? Can you do it with lithium niobate? And first, we need thin films of lithium niobate on substrate. And here's a brief history, I guess, of the first thin films that were realized. In fact, when I was postdoc at Federico, I got some of these films in 2003, and great fun filming them. Nothing ever worked. Film is an amazing tool to make beautiful pictures, but they can never edit them, get rid of gallium. So if you know how to do it, let me know. And you can make some fun devices with it. But anyways, these thin films were really, really tiny. And so we couldn't really make good devices. Fortunately, there's this company, NanoLand in China, that came up and they're basically a major provider now, but there's many other providers of thin film lithium niobate that's made using smart cut process. We take the lithium niobate, it's grown in the Chukasky process, similar with silicon, we cut it in wafers like salami, then you come in and implant some ions, okay? And then these ions actually damage layer of lithium niobate below the surface. Then you prepare another substrate with silicon oxide and silicon, you bond this lithium niobate wafer on top of it. You thermally stress this layer so that actually the structure breaks at this damaged region, and then you polish it to make it nice and smooth and flat, and that's it. This is called smart cut ion slicing process. Same process is used to make silicon insulator and many other actual platforms. And so with that actually thin film available, then people really started looking into ways to actually make integer photonic devices. And then you have two choices. One is, not many choices, but there are two main. One is monolithic approach, which really means I'll take this thin lithium niobate and I'm going to etch it to make a waveguide resonator directly into niobate. It maximizes overlap between optical fields and nonlinearity, which reduces thresholds, electrical and optical. Or hybrid heterogeneous approach. So actually, this one is pursued by Tobias here as well. You can have self-connected waveguide with the film lithium niobate on top. And so it's really, jury is still out which one is going to be better. We are going to bet on this one. I think Tobias is betting on both. It's probably a good idea to bet on both. What we did then, thanks to some grumpy referees who didn't believe this properly scale, we actually figured out, rather Mian was positive at the time, fabrication recipes to make ultra-low loss lithium niobate waveguides. And at that time, we could make lithium niobate waveguides with loss of about 3 dB per meter, which is actually orders of magnitude better than was done by up to that point. And this is a very correct point. The main reason why we were able to do this is because we had really high tolerance to pain with dealing with diamonds and etching diamond. And so, we've unleashed a lot of know-how that we figured out then to make this happen. More recent work in the group, we actually can go to 1 dB per meter, which is about 3 times better, which for many applications is actually good. And in Tobias also, we demonstrated that actually the limit of this platform is about another factor of 10. And beyond that, if you want a high QE, you need to either get better lithium niobate, or we can come up with actually better oxides possibly as well, and so on and so forth. Okay. And then with this kind of different platform, this is like shameless plug. In my group, we were able to demonstrate all kind of neat devices simply by just all of them outperform their bulk counterparts because we can tightly confine light inside optical nonlinearity and have very nice overlap between optical photons and optical microwave photons that gives rise to amazing modulators, to amazing frequency phones that we heard about, and some new other devices that I'm not going to have a chance to talk. Lithium niobate is interesting for all kinds of other applications. I'm particularly excited by this collaboration we heard about. Christina, it's probably the most prolific collaboration ever had, like in the generation of terahertz signals and detection of terahertz signals using lithium niobate. We are also exploring regarded photonics, some sources for continuous tomography, and so on and so forth. I do want to advertise another text that I introduced my conflict of interest. I do want to advertise our startup, Hyperlight, that's actually commercializing this technology. So they make high-performance modulators you can buy off shelf. Some of these are already, you can find in Tor Labs and Aritsu components, for example, for high-performance characterization equipment. In OFC conference a few years ago, there was a demonstration discussed in a panel presentation by Arista Network. These are the pluggables these are actually devices, transceivers that convert signals from electrical domain to optical domains. So basically, you put this thing into a computer rack, and on one end, you have electrical 1s and 0, on the other, optical 1s and 0. And by actually replacing silicon photonics chip with a lithium niobate photonics chip, as shown here, they were able to show reduced power consumption tremendously, which is actually a big deal in this community. Because you may know data centers and all infrastructure around AI is burning tons of power. And that's actually one of the big problems. Okay, and also Hyperlight has all of their fab in foundry, commercial large-scale for overseas foundry, and also they offer multi-project wafer runs if you're interested. So going back to why we're here, is this platform that I promised you, that are going to fix all of the issues with lithium niobate, with the diamond. So one is multiplexing, and I'm not going to go into details, but If you're familiar with wavelength division multiplexing in classical communication, the idea is same here. We can take silicon vacancy, if we know how to shift the emission, unlike in atoms, right? Well, in atoms again, maybe you can use stark shift, emission wavelength. Here we will use modulators to address this. We can actually have silicon vacancy and make a slightly different color. Okay, you can shift them, and then that allows us to using different colors actually multiplex our communication channel. So if each communication channel is slow, now we got hundreds of them, we can actually have very high communication rates. And so this is some calculation my student has done. Actually, I didn't provide a reference, but this is an archive you can find out this video. It's theoretical experimental. In order for this to work, if you're multiplexing things and chip better, your interface with fiber will be really good. And so I told you for diamond, you can do 90+%. In lithium niobate, we apply the same idea in interest of time. We're going to go into details, but we make lithium niobate paper and we bring fiber to it and touch it. And we can get invisible around 1 dB loss, which is decent, but you know, as soon as I show you something in dB, it means it's large. I would very much like this to be like 99% efficient. And here it said we should be able to get there, and so we are actually working on this. But at the moment we have 1 dB, which is good enough for some preliminary experiments. So we can multiplex, we can get like on and off chip efficiently. We also can integrate laser on lithium niobate. I'm not going to talk to you about this today. And so now we need to do multiplexing, so we need switches. And so here is just an example of Mach-Zehnder kind of based switch. This is, again, maybe slide for specialists. Our modulators in Visible have so-called V-pi voltage, which is the voltage required to get the 2 arms of this Mach-Zehnder out of phase, right? It's about 0.5, it's half volt. We can actually go much less than that also if you trade off for some loss issue. And then if we go to shorter and shorter wavelengths, actually this is the trade-off. If you make, you go even around 0.4 volts if you actually allow for a little more loss in the interferometer. And also by going to shorter wavelength, you can also further reduce this. And since this was actually submitted in an archive, we and others have also done much better. The bottom line is, you know, I think 0.1, 0.2 volts is not out of question actually some of these devices in visible wavelength range. And this kind of just puts some of this work in perspective, but this field is moving so fast that it's probably outdated charts are not going to bother you. But essentially compares speed and voltage, and optimal point is here. You want to operate as fast as you can, but without spending any energy. But that's of course not easy. But we're kind of moving slowly as community into this one. Okay. So now, we can switch to move light left or right. We can multiplex. We know why we want to multiplex, so we can get light out in fiber. So now how about fixing that wavelength, right? So for that we will use phase modulators. So in order to work on this inhomogeneous product. And the way this works is actually relatively simple. If I have a phase modulator and phase of any signal, you know, I should have written this less fancy. It's 38 times cosine phi t minus omega t. Something that you learn like engineering for all the first year. Maybe it's fun even in elementary school. I don't know. So if this changes, if phase is changing linear in time, that looks like frequency times time. So that becomes frequency shift. So if I can have phase change that's ramp in time, then I actually can change the frequency of light. And so there's 2 ways you can do it. Because you cannot have this ramp go infinitely forever, right? So what you can do, you can actually use this sawtooth signal. So you need to time it so that, you know, like, and you need to be able to turn modulator off real fast. And so this sawtooth then approximate this thing. This requires very high dynamic microwave electronics. Or you can use simple harmonic drive, and you have sine wave, and you rely on the slope of sine wave to be line, which is not true, but it's close enough. And so we did both. For example, this first part is spectral shearing. We use sine wave. We have phase modulator. We send single photons from here, apply micro signals in this direction. We make sure this just shows where optical signal is. Okay, this is classical field, but we've done the same thing in signal photon fields. And then we park our optical pulse on a rising edge of sine wave, and we get shift about 5 to 10 gigahertz. up in frequency. If you park it here, you get shift back. You were able to shift up to 35 gigahertz each way, which is plenty good. Like the inhomogeneous broadening is less than 50 gigahertz. But as you shift more and more, you start feeling these like nonlinearity of silicon. On sign, and that's some issues. So the drawback of this is, so this works really well actually. It's very simple. Drawback is that you need pulses because your optical pulse needs to be shorter than the rise or falling edge of your sound wave. And our pulses, as I told you, in silicon vehicles is very long. So that's actually limited efficiency. If you have short pulse, this works beautifully. If this was 50-second short pulse, you could shift this by hundreds of gigahertz, no problem. In fact, we can demonstrate that already. But the question is, can I do this with CW light, which is kind of our single photons are a little bit like continuous wave light. And then you can use this Ceradyne approach where we use sawtooth. Okay, and then we can get really nice shift on the order of like gigahertz. We can like almost no loss, and then we can have shift up to like 15 gigahertz in this case. But this is not CW light. Okay, we're shifting the color of CW signal. Actually, not quantum signal. And this is still better, even though it has pretty high loss. It's still better than alternative technique, which is to use so-called IQ modulator specialists to kind of do the same thing. Okay. To kind of generate two sideways and then filter to one and keep the other one. So this is still efficient. And if you had better electronics, you would be able to actually make this more flat. And you can learn more. Yeah, there's no reference, unfortunately, but there's this paper is also in archive as well. So another way how you can shift light, the CW light is, and it's kind of more fun way, but maybe going to be less applicable in the moment, but you'll see, is to use photonic molecule. Essentially, to use photonic two-level system to control the color of light. And the way it works is following. We take two resonators, optical resonators, and couple them. And then, so this is transmission of one resonator. You see these dips, these are resonances of the resonator. When you couple two resonators, these resonances split in two. Okay? And so the nice thing about the system is that actually this splitting we can address, in our case, using electrical signals. Because these two resonators are made in lithium niobate. This is how they look like. So the lithium niobate two ring resonators with two optical waveguides to bring light in, RF electrodes. And what happens, the idea is you will put light in this optical resonance, apply RF field, and this light will jump out. And then we collect it from there. And so that's how we shift the color of light. And it can be done with pulses for CW. And so maybe I'll just show you a result in the interest of time. So this is the data that shows one particular system where we input the light in one resonator, this frequency, and then we turn RF on, and you see slowly you get more and more light going to the other resonance. And after you apply about 10 milliwatts of RF power, you have actually 50% of light in one resonance and 50 in the other one. So this is frequency domain beam splitter, very interesting for photonic quantum computing. Okay, and then if we keep applying more and more RF, then I can take all of the light from one resonance to another. So in this case, I achieved a shift of 30 gigahertz from one resonance to another. And this can be tuned by applying DC field. Actually, the splitting between two resonances can be tuned. So this can be very nice tunable shifting. The downside is you need to make resonance structure, and that's a little more tricky than making this waveguide. I mean, you can do it, but you need to pay additional attention to it. Okay. Not sure if there is it's here. So maybe now we tackled on these two top points. I will not tell you a whole lot about the third point in the interest of time. I can come back to this if there is interest. This frequency conversion, especially since we had such a nice, wonderful talk at the beginning. I would just say that the idea is to use periodically cold lithium niobate, similar to the one that the first speaker was talking about, to essentially perform frequency conversion of 737 nanometer single photon to 1300 nanometer single photons, and back. Okay. The way this is done is the process of difference in some frequency generation. We can start in some frequency generation, we go from 1300 to, okay, I guess I lost this thing there. Here we go. 1300, let's say 1300 will be read to 737 by providing about 1600 nanometer pump. Okay. So we can take the almost 100% communicate yearly conversion from 3000 nanometer to 737 nanometer light. And the other way around, we can go from 737 to 1300 by applying singular quantum. This process should be efficient and importantly deterministic. So a lot of this, I really like the first presentation, and also Camila is doing here, is a lot of papers in this field. You pull lithium niobate, you measure some conversion, great. And this conversion due to material limitations typically is about 100 nanometers off from where you want it to work. Okay, maybe it's efficient, but it's not where you need it. We have about 10 gigahertz room for error, because we need to go 737 plus minus 10 gigahertz to 1310 plus minus 10 gigahertz. That's it. And then thickness variations in this lithium niobate, I'm gonna skip this. Thickness variations, which is in thin film lithium niobate, is roughly 20 plus minus 20 nanometer variation of starting material, because it's not well developed. That is enough to mess up your fabrication process and performance of these devices tremendously. So typically people make thousands of devices and then cherry pick 5 that work. We were looking into ways to make this a scalable platform, and we have developed this process of that combines a lot of metrology to get information about the thickness variation, and then we use this information to adjust the period of this pole structure so that they work perfectly, basically. And so this is, we do this at a wafer scale, so we take a wafer and we pull it, and the goal is to have 100% of the LED devices exactly the way that we want it to be. They're not quite there yet. We use a lot of epsometry, a lot of measurement before, and then a lot of kind of design strategies to get there. So we are not quite there yet, but basically we do have at the moment, so you highlight it and give more details. It's just a very technical paper. Roughly, you know, we were able, this is a histogram of devices in 2 different wafers that show we get pretty close to 737 nanometers. Okay, we would like this to be a little tighter. We would like to be within kind of phase shifting of a modulator. The reason why this one didn't work so well, even though it's narrow distribution but it's off, is because we figured out that actually ellipsometers in our clean room are not calibrated. We actually can use this process to calibrate ellipsometer, which is not what I want to do. I would much rather have a better ellipsometer and be able to measure the thickness precisely. But it just tells you how sensitive this process is. So I'm really excited to see that also here in EPFL there's a lot of work in CSEM and EPFL actually going in this direction. Okay, if you're up for it, I have another. Yes, okay, so then I'll stop. I'll just say transduction is another topic that we're looking into, but I'm not gonna go into it. I'm just gonna go straight to the end, which I think that one of the people who did a lot of hard work in this space. Shima may be familiar with some of you. No, I have pressure. I would just say that basically we think that this kind of lithium niobate photonic platform really can address the needs of quantum optical interconnects and enable the connectivity to trapped ion fast computers, solid state based quantum computers, and you'll have the maybe quantum transducers. So they based on this couple of resonators in an electro-optic platform. And maybe with that, I'd like to thank the group. And I mentioned people who've done the work already. I'd like to thank collaborators. They also include Christina here and also some funding sources, and of course all of you, especially for giving me extra time. So thank you for that.
Really mind-blowing and also encouraging for those of you who are doing even more for how important this is. So, are there any questions? One question, yeah?
Thank you for your talk. So my question is, when you reach these values of Q factors, tens of billions, so I guess one issue for practical applications, as you mentioned, is the thickness variations. Would be, but also what about the temperature? So I guess for quantum, maybe you could afford keeping it very stable, but maybe for some practical applications like sensing, do you need, you know, laboratory scale to keep it very stable for them to perform, or is something that much?
So you're thinking about thickness variations, so impact on stability of these components, especially since they're so sharp, right? Is that the question? Yeah, so I mean, so for modulators, that is not a huge issue, especially due to some actually rather subtle but important issues with lithium niobate. We actually use heat to bias modulators to so-called quadrature point or null point, depending on application. So they actually heat our friend, but we heat it preheatable. So if small heat variation, we haven't seen any problems. We would much rather not do that and use electro-optic effect, but there's subtle issues that I'm happy to discuss over another drink. And for resonance structures, I mean, so when you have, especially for electro-optic ones, when you apply 1 watt of RF on chip, things do heat up. And so the way we deal with this at the moment is, but you know, also like these, especially frequency combs I didn't talk about today, but they're super robust. You can adjust, you can tune the back, right? And you know, there's, if you like, we do the same thing, but today also they were showing me a live demo of this, and Tobias' lab. Devices tend to be very, very robust. The devices, especially all electro-optic devices, are really kind of linear in terms of light. So we have this additional electric field input that we can use to control. These are not high nonlinear devices like curved frequency combs, but others would be a lot more sensitive in my opinion. So we haven't seen it in a classical lithium niobate, the traditional lithium niobate modulators and components. They have feedback circuits that is always like checking for this, and probably for real application, you would have to actually put that. And in fact, in this transceiver, there are feedback circuits. There's a bunch of detectors on chip that are checking if the modulator has drifted. But it's not you know, it's true for silicon photonics or other platforms. Yeah. Okay.
Hey.
Dimitri.
Hi Marko, great stuff. You know, when I used to know you, used to do all classical devices.
I do, I was a classical guy.
Now you
I also had less great hair.
now you lost the class a little bit and do quantum. When you make this transition, what do you have to do to make this transition? What's the difference when you build like
Why did it do it, or what was the cost of it? This is a very open question. Like, what did we have to change in our maybe approach? Is that maybe the question?
Yeah, I mean, you build the classical devices and then all of a sudden you have to do something with the complement and all that. So what changed? What you have to do?
So we have to pay a lot more attention to losses, minimizing losses, because if you start losing light, you're losing information, and that's not very good. There are protocols that can protect you against it, but it's ideal to have no loss to begin with, and then you can have a very, very robust quantum system. Other thing was you cannot work anymore with traditional photonics material. Almost certainly cannot work with silicon for all applications that I discussed, because you need to go short wavelength, where atoms and ions and qubits in solid state operate. So that means develop a platform. So actually, to me, it was actually a challenge. It was attractive about quantum, that there are all these materials with excellent properties that people didn't address because, I guess they didn't care enough about that. Just, then you need to generate a lot of money because it's very expensive. And getting student is not that hard because it's very, very exciting field, I think. And then, as I said, it's intellectually stimulating, and in the worst case scenario, we have amazing photonic devices that will power the future classical components. So I'm excited about that.
Okay, we also have quite some questions online, so I will also ask you some of the questions from online. So one question, is it possible to do color centers directly in lithium niobate?
Yes, a great question. It is possible. Lithium niobate, in terms of like this, many materials have color centers, but not very many materials have good color centers, good spin properties. So lithium niobate has background spins that can impact that. People are looking for thulium. In fact, quantum memories in thulium, I think it was pioneered by this is Shazan or the guy in Calgary. I'm drawing blank on the name, but anyways, they were some of the first kind of quantum memories in solid state for these rare earths and lithium niobate, classical lithium niobate. So that's an amazing research that continues. So we personally are looking into rare earths and lithium niobate, but really that's about it.
Okay. Are there any other questions from the audience? Yes.
Yeah, there was a question over there.
Yes.
Awesome talk. So my question was regarding like the phase shifters.
Yes.
So I guess like what we need for these systems is like cryogenic compatible phase shifters. Is this right? So
maybe, but keep going.
oh, okay. So like what's the size of the phase shifter represented like in this work, and like can you make this scalable, because this is a big word in this time case.
So I see where you're getting it, so I answer it philosophically directly. It is scalable, that's not both the direct and philosophical statement. I mean, you can make it scale. Is it small? It's not, right? Like how, like depending on how we do it, I missed that whole part. We do it in cryogenic temperatures, and we think we can connect many qubits to one transducer, so that's fine. Phase shifters that I discussed about don't have to be cool, because we think that actually, despite me showing the diamond lithium niobate, at least in first maybe a year or 2, 3, this is going to be two separate devices, diamond and detectors will be in the fridge, and then very efficient interface will go between to connect them to photonics. Eventually, we would like to do everything, and then they incorporate 12. So 2 centimeters if you want very low VPi, which we want. What are the alternatives? Alternatives would be probably barium titanate, right, or material with higher electrolytic coefficient. Though there's all kind of problems with barium titanate at the moment, but if you can grow high quality barium titanate material, that would be very exciting. There's strontium titanate, it's really exciting material, also, you know, but these are all important material science endeavors, and it can be relatively straightforward to transition to them if they turn out to be better.
Thanks so much.
Yep.
Okay, so maybe in the interest of time, and then people can still ask a lot of questions. Just one closing question from my side. So obviously, all of these devices they need a lot of RF, right? So RF. So are you going to start doing electronics as well?
This is a tough question. So I was joking today, like whole photonics field, when you talk about power consumption, this you always focus on chip, and you forget that there's like 3 racks of electronics and a bunch of lasers and whatnot. So of course, for like Hyperlight that is working with partners who are focusing on, there's 2 approaches. You could do vertical integration, which may or may not be a good idea, or you can specialize one thing and then work with partners. So companies work with partners that provide high frequency electronics that goes up 110 gigahertz. It's not cheap, but such is life, right? We are not doing this, but if people are interested in doing this, I know actually there's some work. 2 artists doing some amazing trial, CMOS work here. I'm always looking for people that would be interested in maybe powering some of these devices. So right now we're not doing that. We're buying it with expensive equipment.
We give it away for free.
Huh?
We give it away for free.
You give it for free?
Of course.
Everybody encourages you now.
Okay, thank you so much, Marko. Let's thank you.